2 experiments. Different materials, different temperatures, run on different days. Every measurement carries random noise, a fingerprint that never repeats. These 2 carried the exact same noise, bump for bump. That is impossible. Which meant someone had made them impossible on purpose. His name was Hendrik Schön. In the spring of 2002, this 31-year-old physicist at Bell Labs was publishing a paper in Science or Nature roughly every 8 days. He had built the smallest transistor ever made. He had turned plastic into a superconductor, and almost none of it had happened. That is not a metaphor. The experiments he described did not take place. The materials did not behave the way he said. The graphs that stunned the physics world were, in many cases, drawn by hand and typed into a computer. For 4 years, nobody caught it. To understand how that is possible, you have to understand what Schön looked like from the outside. Because from the outside, he looked like the best young scientist alive. He arrived at Bell Labs in Murray Hill, New Jersey in 1998. He was young, German, quiet, and easy to overlook in a hallway. Bell Labs was not an ordinary lab. It was the place that had produced the transistor, the laser, the foundations of the information age. 6 Nobel Prizes had come out of that building. If you worked there, you were expected to be brilliant. Schön was better than that. He was fast. And speed, in science, is a kind of magic. A result that takes everyone else 2 years, arriving in 2 months, does not just impress people. It reorganizes the field around you. Grants follow the person who moves fastest. Attention follows. Belief follows. Schön moved faster than anyone, and the belief came pouring in before anyone thought to check the foundation it was resting on. Within 2 years he was averaging almost a paper a week in the most prestigious journals on Earth. In 2000 alone he published 8 papers in Science and Nature. Think about what that means. Most physicists spend a year, sometimes 2, chasing a single result worth publishing in those journals. Schön was producing them faster than his colleagues could read them. And the results were not small. He claimed he could take ordinary organic materials, the kind of carbon-based molecules that make up plastic, and coax them into doing things that silicon does. He claimed he had built a transistor from a single molecule. He claimed he had made organic crystal superconduct, carry electricity with 0 resistance. If any of it were true, it would have rewritten the future of electronics. Prizes followed, awards. A mentor at Bell Labs who co-authored his papers and vouched for him. Whole research groups around the world dropped what they were doing to build on his findings. And here is the first strange thing. They couldn't. Lab after lab tried to reproduce Schön's results. They followed his methods exactly. Nothing worked. The materials refused to superconduct. The transistors refused to switch. For a long time this did not look like fraud. It looked like difficulty. Schön's technique must simply be very hard to master, people told themselves. He must have a delicate touch, some feel for the materials that others lacked. That assumption protected him for years. Think about how reasonable it sounds. When a genius does something and you can't copy it, the obvious explanation is that you are not the genius. The failure feels like it belongs to you. You go back and check your own equipment. You question your own hands. You do not, at first, question the famous man whose paper you are holding. There is a deeper reason the doubt didn't come. In science, the burden of proof does not sit evenly. A published paper in Nature carries the weight of the whole institution behind it. Your failed attempt in your own lab carries only you. So when the 2 collide, the paper usually wins. The scale is tilted before the argument even begins. So the physics world kept chasing. Millions of dollars in research funding went into rebuilding experiments that had never existed. At least a dozen labs burned time on it. Graduate students spent months of their lives, months they could never get back, trying to reach a summit that had been painted onto the sky. Now hold on to one detail because it will matter later. Every experiment produces noise. When you measure a tiny electrical current, the signal never comes out clean. It jitters. It fluctuates in a random, messy way that depends on the exact material, the exact temperature, the exact moment. That noise is like a fingerprint. No 2 measurements should ever produce the same one. Remember the noise. The people who first felt something was wrong were not investigators. They were just careful. In early 2002, 2 researchers named Lin Lu and Julia Su were preparing a patent. Their work leaned on Schön's published data, so they were reading his papers closely, more closely than a casual reader ever would. On April 19, 2002, sitting in a meeting with their patent lawyer, They noticed something they could not explain. A figure in one of Schön's papers looked familiar. Too familiar. It appeared to match a figure from a different paper describing a different experiment. That was the thread. Someone pulled it. Word reached a physicist named Lydia Sohn, then at Princeton. She had been uneasy about Schön's work for a while. His data was, in her word, too perfect. So she went looking, and she found 2 experiments, run at completely different temperatures, on what should have been different systems, that shared the exact same noise. Not similar noise, identical noise, the same random jitter, bump for bump. Remember what noise is. It is the fingerprint that is supposed to be unique every single time. 2 experiments cannot produce the same noise by chance any more than 2 strangers can share the same fingerprint. If the noise is identical, the data was not measured twice. It was copied. When the editors of Nature put this to Schön, he had an answer ready. He said he had accidentally submitted the same graph twice. A clerical slip. An honest mistake. It might have ended there. It didn't because of one more person. Paul McEwan, a physicist at Cornell, heard about it and went hunting through Schön's other papers. And he found the same noise again, in a 3rd experiment, a 3rd supposedly independent result carrying the identical fingerprint. 1 duplicate might be a mistake. 2, a strange coincidence. 3 was a pattern, and a pattern is a confession. McEwan kept going. He gathered the most damning examples he could find and sent them where they needed to go. In May of 2002, Bell Labs convened an outside committee, chaired by a Stanford physicist named Malcolm Beasley, to investigate one of its own. What the committee found was worse than anyone had guessed. When they asked Schön for his raw data, the original measurements every scientist is supposed to keep, he couldn't produce it. He said he had deleted the files because his computer's hard drive was full. He kept no lab notebooks with usable records. The experiments that had dazzled the world had left almost no trace that they were ever run. Some of the fabrication was almost childish once you saw it. Data that was supposed to come from a physical measurement was mathematically too perfect, following clean curves that real, messy experiments never produce. In one case his numbers matched, down to the smallest random bump, across results that had no business matching. He had taken a single curve and reused it to represent completely different physics. There was one more detail that turned suspicion into certainty. Real measurements come with error bars, the little marks that show how much a number might be off. Nature is uncertain, so those bars have a certain looseness to them. Schön's error bars were, in places, too clean, too neat. They followed perfect mathematical shapes that no messy laboratory ever produces. It was the signature of someone who had generated numbers from an equation rather than a machine, and then dressed them up to look measured. The committee examined 24 separate allegations. It found clear evidence of scientific misconduct in 16 of them. His co-authors, the colleagues and the mentor whose name sat beside his on those papers, were all cleared. The committee concluded that Schön alone had done it, quietly, at a desk for 4 years. In September 2002, Bell Labs released the report and fired him the same night. Now pull back because the interesting question is not what Schön did. It is why it worked for so long. He was not a master hacker breaking into a secure system. The system that failed here was trust, and trust is not a flaw in science. It is the load-bearing wall. Peer review, the process meant to catch bad work, was never designed to catch a liar. A reviewer reads your paper and checks whether your reasoning holds and your conclusions follow. A reviewer does not fly to your lab and demand to watch you run the experiment. The entire structure assumes you actually did the thing you said you did. Schön understood that, maybe without ever putting it into words. He gave the field exactly what it wanted. Superconducting plastic, molecular transistors, the breakthroughs everyone was already hoping for. When results confirm what people want to believe, the skepticism relaxes. His mentor wanted the papers to be real. The journals wanted the papers to be real. The reviewers, reading beautiful clean data that pointed exactly where the field was heading, wanted them to be real. Psychologists have a name for the pull underneath all of this. Confirmation bias. It is the quiet tendency to accept evidence that fits what you already expect and to scrutinize evidence that doesn't. It is not stupidity. It is a shortcut your brain uses on everything, all day, because checking every claim from scratch would be exhausting. A liar who understands that shortcut does not have to break your defenses. He only has to hand you something you already wanted, and let your own mind lower the drawbridge from the inside. There is a second layer to it, quieter still. When a claim is spectacular and it comes from a spectacular source, doubting it is expensive. To question Schön was to question Bell Labs, the journals, the prize committees, the whole chain of people who had already blessed his work. Being the one skeptic in a room of believers is lonely, and it is risky, and most people, understandably, would rather not. Silence is safer. That silence is the exact space a fraud lives in. And that is the part that should follow you out of this story. The failure that lets Schön get away with it is not some rare defect in scientists. It is the ordinary machinery of your own mind. You trust confident people. You trust results that fit what you already expected. When something feels too good to be true, but you badly want it to be true, the wanting quietly wins. You lower the bar without noticing you lowered it. The labs that couldn't reproduce his work blamed themselves for years rather than doubt the star. That instinct, to assume the impressive person is right, and you are the one falling short, is in you too. It is how a room full of the smartest people alive spent millions chasing something that was never there. Science eventually corrected itself. In 2004, the University of Konstanz, where Schön had earned his doctorate, revoked his PhD. Papers were retracted from Science and Nature by the dozen. The field moved on. And in a strange twist, some of the breakthroughs he faked have since been achieved for real by honest researchers. But it took two careful women preparing a patent, an uneasy physicist who trusted her own gut, and a stubborn man at Cornell who went looking. It did not take a machine or a rule. It took a few people willing to distrust a result that everyone else adored. Go back to the beginning. A physicist publishing a triumph every 8 days, holding the future of technology in his hands, admired by everyone. From the outside, the best young scientist alive. The signal looked perfect. And that was the tell. Because in the real world, the one thing a genuine experiment never gives you is a fingerprint that comes out exactly the same twice.